Okay, for my part, I will explain the hexadecimal conversion. Alright, let's break down how this snippet of assembly code works step by step. First, we have instruction li register v04. What does it do? It loads the syscall code for printing a string, code 4, into the register v0. This tells the system that we want to print something. Next, we have LA register A0 hex label. This one loads the address of a label called hex label into the register A0. We- The label likely holds a string, so now register A0 points to the string we want to display. And finally, the instruction syscall is like pressing enter after setting everything up. It uses the syscall code in register V0 and the address in register A0 to execute the printing operation. And so the text hexadecimal gets primed to the console. Okay, now let's dive into how this piece of assembly codes, extracts, and prints the height nibble of a hexadecimal number. First out, we use SRL register T1, register T04. This instruction shifts the value register T0, our input number, right by 4 bits. This isolates the height nibble or the first 4 bits and places them in register T1. Next, ND register T1 registers T1 0x5 applies a bitwise AND operation with 0 multiply 5. This ensures that only the lower 4 bits of register T1 are kept, clearing out any extra data. Here we use AD register T1 to register T148. Adding 48 converts the numeric value in register T1 to its ASCII equivalent for digits 0 through 9. Now, this is where the branching logic comes. The instruction BLT register T1 58 print height checks if the value in register T1 is less than 58. Remember, in ASCII, the character for 0 to 9 fall between 48 and 57. If register T1 um, is less than 58, it's a digit. But no, and we jump to the print height level to print it. And if register T1 is not a digit, that means the value corresponds to the letters A through F in hexadecimal. So to handle this, we add 7 to the value uh, in register T1 to shift into the correct ASCII range for in to F. And that's how the code process and prints the height nibble of a hexadecimal number. Now let's look at how the program actually prints the height nibble after processing it. First, we see the instruction move register A0, register T1. This move the ASCII value of the height nibble which is stored in register T1 into the register A0. Um, why? Because register A0 is the designated register to passing data to the syscall that handles printing. Next, we have LI register V011. This loads the syscall code for printing a single character into the register V0 register. In MIPS, syscall code 11 tells the system to print the character stored in register A0. So, for lastly, we call syscall. This tells the system to execute the operation we have set up, print the character stored in register A0, which is the height nibble ASCII equivalent. Okay, for ND register T1, register T0, 0 multiply F, first we use the ND instruction to mask the lower 4 bits of the register T0 register. This isolates the low nibble and stores it in register T1. Think of it as extracting just the hexadecimal digit we are interested in. For add register T1 register T148. We add 48, which is the ASCII value for 0, to register T1. This converts the nibble to its ASCII equivalent if the value is a digit between 0 and 9. So for BLT, register T1 58 print low. Here we check if the value in register T1 is less than 58. Why 58? That's the ASCII value for the next character of the 9. If the value is less than 58, it's a digit. So we jump to the print low level to display it directly. And for AD register T1 register T17, if the value is greater than or equal to 58, we know it represents a letter in the range A to F. To adjust the ASCII value correctly, we add 7. This shifts the character from 0 to 9 to A to F and A to F. Okay, so let me walk you through another snippet of MIPS assembly code and its MIPS purpose. Okay, so for move register A0 register T1, the instruction move the ASCII value of the low nibbles stored in register T1. This prepare the value for printing. And for LI register V011, the LI instruction loads the value 11 into register V0, and this value is the syscall code for printing a single character. And for syscall, it's still the same. This is the system that executes the printing of the character stored in register A0. And for LI register V04, here the value 4 is loaded into register V0. This is the syscall code for printing a string. And LE register A0 new line, the LE instruction loads the address of the string labeled new line into register A0. This string contains a new line character. And for the syscall, the system call execute the printing of the new line character, ensuring that the output is separate from any following text. So this code prints the ASCII value of the low nibble followed by a new line to format the output. So we look to the next slide. Okay. Okay. For this code, its purpose of printing a new line. It prints an additional new line character after the hexadecimal output. Why is this done? This is because to create an extra space in the output, to make it more readable and visually organized. Okay, let's go to the next slide. Okay, um, for for this, ID register S01. This instruction is an increments the value stored in register S0 by 1. It's commonly J input loop. This okay. The is currently counter. It's commonly used as a counter in loop, and for the J input loop, this is an unconditional loop jump instruction. It directs the program flow to the label input loop, which marks the start of the loop or a specification of the code. So for that input, this is a label. Labels in assembly code act as markers for section of the code. The program can jump to this label when needed to continue execution from this point. So this could represent a part of a loop mechanism. The add instruction update the counter, and the J instruction ensures the program repeats the loop. So the done input label marks a point where the program could exit the loop or transition to another part of the code. And for the last line is we exit the program. The value 10 in a register V0 is used to indicate the exit system call to exit the program. So that's all from us. Thank you.